Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're going to be solving Leetcode problem 1361, validate binary tree nodes. You have n binary tree nodes numbered from 0 to n-1, where node of I has two children, left child of I and right child of I. Return true if and only if the given nodes form exactly one valid binary tree. If node I has no left child, then left child of I will equal -1, and similarly for the right child. Note that the nodes have no values. Note that the nodes have no values and that we only use the node numbers in this problem, which just makes this question even more annoying. So let's look at some of the examples that Leetcode provides us and think about whether or not this is a valid binary tree. So in this question, as we can see, this is a valid binary tree. Why? Well, there's only one root. Each, node has only one parent, and it has at maximum kind of two children. So this is a valid tree. This one, however, is not a valid tree. Why? Well, this node 3 has two parents, 2 and 1. We can only have one parent for a node, so this is not a valid tree. What about this one? This looks like it could be a valid binary tree, but notice that this direction here is bidirectional, which means that we essentially have a cycle in our tree here, and you're not allowed to do that. Typically in trees, you have, a parent which has a left and a right pointer, but you don't have a pointer up to the parent. So this is not a valid tree. So this question is more of a question of building your binary tree, which is the first step of this question, is to actually, build the tree, or at least build whatever you can of it, because we'll see that there's a lot of edge cases here. So we're going to try to build the tree. And the second is going to be to validate whether or not our tree is actually valid. And there's going to be 3 edge cases that we want to watch out for. The first edge case is going to be cycles, right? This is the case where a child points to its parent and then the parent points to the child. Obviously, we can't have that. The second thing we want to watch out for is actually going to be multiple roots. Multiple roots, right? What if there's just another node kind of like 2 floating out here and it's not connected to anything? Obviously, this is not a valid tree because you have multiple nodes that could be the root of our tree. So this 2 isn't connected to anything, and therefore we want to watch out for that. So we want to make sure, essentially, starting from whatever we think the root of our tree is, we want to make sure that we can actually visit all the nodes in the tree that we have given to us. And if we can't visit all of them, then that means that there's one kind of just floating in space, and therefore it's not a valid tree. And the last thing we want to watch out for is going to be multiple parents. Parents. And obviously this is this case here where 3 has 2 parents, which is not allowed. This isn't a graph. So we can only have one parent for each node. And the only node that's allowed to have no parent is going to be whatever our root node is, because obviously the root does not have a parent. It is the entry point into our tree. So that's what we want to do. We want to build the tree, and then we want to validate it. And we want to watch for these 3 things as we go through. It's quite a meaty problem. This question is more about the edge cases and how you handle them as opposed to the actual logic. Actually validating the tree isn't that bad. It's just making sure that all 3 of these things are, not violated that makes this question annoying. It's more of technically difficult to implement than it is actually conceptually. So let's go to the code editor and type this out. It is quite a long and meaty question, so we're going to break it down line by line. I'll see you in the editor. Okay, we are in the editor and we need to write the code for this. Remember that we essentially need to build a binary tree and validate whether or not it's valid given the criteria that we have. So we don't have the time in an interview setting to actually code up, a binary tree class and then a binary tree node class and all that nonsense. So what we're going to do is we're going to mimic a binary tree by simply using a dictionary to mock the binary tree. And what we're going to do is we're going to have 2 dictionaries, one storing the relationship between parent to children and then we're going to have children to parent. So that way we know all of the relationships in our tree. So what we want to do is define those two dictionaries. So let's do that. So we're going to say parent to children. We're going to say collections.default dict list. And obviously it's a list as the value because a parent can have multiple children. And then we're going to have child to parent. And this is going to be a dictionary. And that's what we need to do. So now we actually need to build the graph. So remember that n represents the, each individual node. And then left child of, I guess, I, where I is one of these n nodes, will represent the, left children for that node, and then the right children for that node. So we're going to say for node in range of n, so we need to build our graph, our tree. We're going to say that left is going to equal to whatever left child of node is, and then we're going to say the right child is going to be whatever right child of node is. Now, remember that a node can have, an empty left or right child. So we need to account for that. So we're going to say if left does not equal to -1, and remember -1 is if the node has no left child. We're going to say, okay, if there's a relationship, then we need to say that parent, so the parent of our node the parent is the node, and the child is obviously this left. So we're going to add to our parent to child relationship. We're going to say the node is the parent, and we're going to append to it that we have, a left child. Now what we need to do is we need to actually double check that the parent is not already part of the child to parent dictionary for, this node left here. Because if we have that, then we have a cycle. So we're going to say, let me not mess up my indentation here. We're going to say if left not in child to parent, we're going to say child to parent of left equals node. And what this is doing is making sure, I think I said cycle earlier, sorry, disregard that. Essentially what we're doing is we're checking if this node is not already in the child to parent dictionary. If it's already in there, that means that this node left has another parent, and we're in this case here where a node has multiple parents, which obviously isn't valid. So if the node is already in the child to parent dictionary, that means that it already has another parent, and therefore we have two parents. That's not allowed. So if it's not in there, that's fine. We can add it to the dictionary. But if it is in there, then we simply need to return false, because we have the case where we have a multiple parent situation, and that's not allowed. So we're going to do the same thing for the right node. We're going to say if right does not equal to -1, so basically if the right child exists, then we need to reflect that in the parent to child dictionary. So parent to children of node, we're going to append that right child. And again, we need to make sure that this node right doesn't have multiple parents. We're going to make sure that this node here is its only parent. So we're going to say if right not in child to parent, we're going to say child to parent of right is going to equal to the node. Otherwise, we have the case where, again, we have multiple parents. That's not allowed. We're going to return false. So at this point, we have built our tree, and we have taken care of the case of multiple parents. Here, we can be sure that at least the case of multiple parents is taken care of, so we don't have to worry about that going forward. Now what we need to do is make sure that there's no nodes kind of just floating in space, unconnected to anything else. For example, like we had this tree here, which is valid, but what if there was a node like 4 just floating out in the distance here? Then this would not be a valid tree because all of the nodes are not connected, and now we have like 2 roots. The 4 could be a root and the 0 could be our root. So therefore, we need to check that only one node in our graph actually has no parent. So what we're going to do is we need to figure out what our root candidate is, because that's where we're going to start our search through the final graph to make sure that we can actually visit all the nodes. So we're going to say root candidate is going to be none. And we're going to be double checking that we can actually visit, that there's only one node that doesn't have a parent, because we can't have multiple roots, right? So we're going to say for node in range of n, we're going to say if node not in child to parent, basically if the node is not in child to parent, which means that this node doesn't have a parent. Remember that the root node is the only node that's allowed to not have a parent. So if the current node that we're working with is not in the child to parent mapping, that means it's a potential candidate for root candidate. But not so fast. We need to make sure that root candidate is actually none, because if there's another node that could be the root, then therefore we have found two nodes with no parents, and therefore we have two nodes that could be the root, and that's not a valid tree. So we're going to say if not root candidate, that means that we haven't already found a root candidate. So we can say root candidate is going to be equal to our node. Otherwise, if we've already found a root candidate and now we found another node that doesn't have parents, we have to return false, because that means that there's two potential root candidates, and that's not allowed. So we're going to return false here. So at this stage, we have essentially found a root candidate, but turns out we haven't actually found a root candidate, because it's possible that there is no root candidate. So we actually need to check if root candidate is none. Basically, if we weren't able to find a root candidate for some reason, then we need to return false. So that will take care of finding the actual root. Now what we need to do is make sure that starting from the root, we can actually visit all the nodes and we don't get caught in some sort of infinite cycle here. So we want to use a visited set to basically keep track of the progress through our tree, because remember, we're using graphs, not a graph here, sorry, we're using dictionaries, so we could potentially get caught in an infinite cycle. If we were using, just a standard graph, so I keep saying graph, if we're using a tree data structure, then we'd only have the left and right pointers. We couldn't go up the tree on accident, but since we're using this dictionary based way to represent the tree, then we could accidentally get caught in some sort of cycle. So we need the visited set to actually tell us where we've been. Otherwise, we can just use a standard breadth first search traversal to actually build this graph tree. Sorry, I keep saying graph. We're going to say Q is going to be just a standard Q here. So we're going to put in the root candidate, because that's typically how you do a breadth first search through a tree. You start at the root and then you just visit all the nodes. So we're going to say while Q, so basically while we have something to process, we're going to say that the current node is going to be equal to Q.popLeft, and we're going to say visited.add whatever the current node is. Now what we want to do is we want to visit all of the children from this current node. So we're going to say for child in parent to children. So the parent node is our current node, and we want to visit the two children. We're going to say if child, let's see, child to parent of node does not equal to the current node. So basically what we want to do here is to check whether or not the node that we're actually going to, its parent is actually the current node. Although I think this might actually be extraneous because we've already checked for the double parents, but I'm just going to leave this in and I'll double check at the end if we actually need this. But essentially we just want to make sure that our child node here, sorry, this should not be node, this should be child. So we want to make sure the child that we're working with, its parent is actually the current node that we're at. So we want to make sure that there's that relationship actually exists. And if it doesn't, if this child's parent is pointing to something else for some weird reason, then our our tree is not valid, and we need to return false here. Like I said, this question has so many edge cases and so many ways where you can get caught in a trap that it's really annoying, and you're gonna have to be very, very careful when implementing this. if this, statement doesn't fire, then we can continue through processing. So we're going to say q.append child, and that will basically go through the entirety of our tree here, and we'll be able to validate it that way. And the last thing that we need to do is we just need to return whether or not the length of visited equals to n. So basically, when we did our full traversal through our tree, were we able to visit all of the nodes? And if we weren't able to visit them all, then something went wrong somewhere, and this is not a valid tree. So let me just run this, make sure that I haven't made a syntax error, which I seem to have. Line 13, if left, not in. Okay, there we go. And okay, cool, let's submit this, and it works. Cool. Let me just double check that we actually need this line here, because I think we already checked for that. Let me just double check this, kind of debug it as we go. And okay, cool. So we don't actually need to check whether or not the child's parent matches the current node, because I think we already do that up here, making sure that the actual relationship is fine. So yeah, that you can get rid of that line actually, or you can leave it in, it doesn't really matter. Okay, cool. So what is the time and space complexity for this god-awful problem? So to build the graph is obviously going to take, big O of n time, where n is the number of nodes in the graph. So that is going to be the, part there. To find the root candidate, we're going to have to go through a range of n. And again, this is going to cost big O of n time. And then to perform your BFS through the tree is also going to be big O of n, where obviously n is the number of nodes in the tree. So your total runtime complexity is going to be big O of 3n, but we know that asymptotically this is the same as big O of n, so we just write big O of n. Space complexity wise, we have these two dictionaries which basically map the relationship between all of the nodes here. And I believe in the worst case, what could end up happening, and I'm not sure on this one, is that every node is connected to every other node in the worst case, which means that our space complexity could be, in the worst case, big O of n squared, because every node would be connected to every single node. So it'd be like a weird graph structure where like every node is connected to every other node. And in that case, it would be big O of n, n components times n minus 1 connections. We get big O of n, big O of n squared space complexity for this one, because of how complex the graph could potentially be in that worst case. So I believe that is your space complexity. I'm not 100% sure. I think that would be the worst case, where your graph is like connected like that. If that's not possible, then it should just be a standard big O of n. But I think to stay on the safe side, I want to say it's big O of n squared, where basically each node is connected to every other node in the graph. Therefore, you get that, big O of n squared space complexity in the actual graph structure here that you have to store. So that's going to be how you solve this problem. Just to recap, because there's a hell of a lot you need to do here. The first thing that you need to do is build this graph. I keep saying graph, I'm sorry. It's a tree. We build the tree here, and we want to make sure that each child only has one parent. We need to make sure of that. We need to make sure that there's no cycles in our graph, and we also need to make sure that there's not multiple roots in our graph. So this part makes sure that we don't have the multiple parents, and it also builds the tree. This part makes sure that there's no multiple roots, and then this part makes sure that we can actually visit all of the nodes and don't get caught in some sort of infinite cycle. Because if we got caught in a cycle, then because we have the visited set, we would break out of the iteration early and we wouldn't actually visit all of the nodes. So that is your three things that you need to check here. Be very careful with this problem. Like I said, there's a lot of edge cases. There's a lot of places you could go wrong. When solving this problem, I would really make sure you understand what each line does and why we need it, because it's very easy to forget this, especially if you see it in an interview. Let's see who asked this question. Okay, it looks like Facebook twice, but okay, so this question, I don't think it really gets asked too much. If you get this in an interview, just hopefully you remembered, build the tree, validate it, and then you want to look for cycles, multiple roots, and multiple parents. But it seems like it barely even got asked, and this is like 6 months to a year ago, and people only reported Facebook twice. So most likely this question is not being asked because of how infrequent it is. I would trust this Leetcode frequency numbers pretty well. But otherwise, yeah, just be very careful with this one. There's a lot of edge cases. Make sure that you catch them all. Otherwise, you're going to be in for a rough time if your interviewer expects the perfect solution, which this question, as you can see, took me a while to figure out. So that is how you solve validate binary tree nodes. Quite an annoying question, but really not the end of the world. It's a medium, an annoying medium, but it's not that hard. If you enjoyed the video, please leave a like and a comment. It really helps with the YouTube algorithm. If you want to see more videos like this, please subscribe to my channel. I make a ton of Leetcode videos and other videos about working in FAANG, so if that interests you, please subscribe. Otherwise, thank you so much for watching. Have a great day. Bye.